not the DS. Send me an email with your ID number and your UMass ID and the ID of the exam. Okay? So regarding one thing about the key, I think I sent email about it, but just to clarify it, if you have exam A as you took exam A for question number 18, in the exam key, I have A, B, C, D, where A is ammonium. I just, for you, when I gave you the exam, I took off that choice to make your life easier, because in NHC it's going to be minus, and then you're going to be asking, is it the highest in absolute or the highest in plus? So I removed that, and this is why the key that I published online for IDA, it will tell you it's D, well, the right answer is C. So I already graded you based on this exam. So your grade is not affected by the key that is online for question 18, for this change in question 18, okay? Now, this is the statistics of exam 1. This is the average of the class, 79.8 something. So if you are in here, you should be worried. You should talk to me, you should do something, okay? Because usually what happens, and I'm gonna tell all of you, that this is the case in every semester for this course. The first exam, the average is 80. The second exam is gonna drop down to 70. Why? Not because I make the exam harder or anything. The material is harder. The material is very new for all of you. Chapter 5 and Chapter 6, and it involves a lot of calculation. This is why I keep telling you, if you have a weak background in math, either get a math tutor or do a revision for one equation, one unknown, and practice as much as you can. Okay? So this is what happens for the class average as we go. Exam 1 is going to be 80. Suddenly it's going to drop to 70 in exam 2. Then it goes up back in exam 3. And then the final is somewhere between 80 and 70. Okay? So what does that tell you? That tell you, if you get 100 in this area, don't think, oh yeah, I'm a great chemist. I don't have to study anymore, because this is what I hear. After exam 2, I see somebody in my office crying. I was like, what's wrong? He or she, I get 100 in the first exam. Now I'm getting 50. I'm like, okay, because you didn't do good. Oh, but I get 100 and I thought I'm a great chemist. No, it doesn't mean that you're a great chemist if you get 100 on the first exam. And the first exam, most of the material you've seen in high school, you've heard about it more, blah, blah, blah. Now, when we get to Chapter 5, it's a new material, it's conceptual, it has also some calculation, it has a lot into it, more than Chapter 1, 2, 3, 4, okay? So please, if you are in this part of the chart, you're great, keep the good going. Don't stop. Don't think you're a great chemist. You will one day. But for the moment, keep the good going. Keep going with the owl. Keep going with the pace of the course as you studied before. If you're in here, you need to do something. You need either to send me an email, meet together, see what's going on. Okay? Now, let's keep going with Chapter 5. So the last time we were talking about melting stuff, evaporating stuff, solidifying stuff, condensing stuff. And we said that when we're measuring is there any game or something today so that the class attendance is lower and even the campus is empty? Is there any special occasion on campus outside of it? Okay. Anyway, let's go back to Chapter 5, okay? So when we're melting something, the equation that we use is different than when we're heating something on the same phase, as heating water from 20 to 90. And we said that the equation that we use to melt something is Q melting the mass times the delta H of the fusion, which is most of the time or all of the time is in joule per gram. Okay? And we only can melt the stuff at its melting point. If it isn't at its melting point, you need to take it to its melting point. Now, to vaporize something, if we're melting something from solid to liquid, it needs energy, so it's going to be plus. If we're going from liquid to solid, it's going to be minus. the Q gonna be minus M delta H fusion, okay? Q vaporization, it is the number of moles times delta H of vaporization. If the delta H of vaporization is in joule per mole, we multiply it by number of moles. If the table or what I give you in the exam is the delta H vaporization is joule per gram, you multiply by the mass because the mass gonna be gram, which gonna cancel the gram there. So be aware of this difference between that sometimes delta H of vaporization gonna be given to you by joule per mole and sometimes joule per gram. Okay, so let's see how we're gonna apply this equation. So this graph is the heat graph of water. What does that mean, the heat graph? It is how much energy I need to take the water from one phase to the other phase. In this case, we're taking 1 gram of ice from minus 50 degrees to vapor, 50 grams of vapor at 200 degrees. Okay? As I said before, we cannot directly jump from solid to vapor. There is one case which we call sublimation, and it happens for CO2, but not for water. So for major cases, to take it from minus 50 to 200 vapor, to take it from ice to vapor, we have to take it through many stages. So the first stage is to melt the ice. I need to take it to its melting point. The melting point of ice is 0 degrees Celsius. So my first step is to heat the ice, and this is the graph of heating the ice, all in here. What is the equation that I'm gonna use? How much heat I need here? Which equation I'm gonna use? So, no, not melting. I'm not melting yet. I'm heating a solid. So it's going to be M times specific heat capacity delta T, where the specific heat capacity of that of ice. So if I'm heating on the same phase, and this is one of the most important thing, and this is the most usual mistake that I see in exams. When I'm heating something and it's still in the same phase, that means solid to solid, liquid to liquid, but I'm heating it up, gas to gas, but I'm heating it up, I use this equation, M times specific heat capacity of that phase delta T. Now, when I get it to 0 and I'm melting it, as you can see that during melting in here, the temperature doesn't change. The temperature is 0. We go from 0 to 0. All the heat that I'm putting in to melt it is just to break the bonds between the particle to take it from solid to liquid. The equation that I'm going to use in this phase is Q melting, which is M times the delta H of fusion. Okay? So now we change the ice from solid. Now in this case it is liquid, but it is at 0 degrees Celsius. Now I want to evaporate the water. To do so, the only way to evaporate the water, to take it from liquid to gas, is to take it to its boiling point. The boiling point of water is 100 Celsius. So, but before, I need to heat it up. So I'm heating the water from 0 to 100, so the Q will be the mass times specific heat capacity delta T. Why? Because I'm heating a liquid. I'm still in the same phase. I'm taking it from 0 to 100 in the same phase. And instead of using the specific heat capacity of ice, I'm going to use the specific heat capacity of water or liquid water. Why? Because I'm now in the liquid phase. Now, we are at 100. We have the water as liquid at 100. Now I'm going to evaporate it at its boiling point. As you can see, the temperature wouldn't change. It's still at 100 when I take it from 100 liquid to 100 gas. So the only thing that I'm doing in here is changing the phase. Now the Q that I'm going to use here equal M delta H vaporization, if the delta H vaporization is in joule per gram. Now, water is in the gas phase. I can heat it up from 100 gas to 200 gas. And again, It's heating in the same phase, so the equation that I'm going to use is Q equal mass, specific heat capacity now of vapor water or gas water, delta T. Okay? So when you're melting, when you're melting, evaporating, condensing, or liquefying stuff, you use different equations than heating something when it is in the same phase. Okay? Now, one thing that I think everybody can see that the Q of evaporation, that the amount of energy I put for evaporation is much, much higher than that of melting. Does that make sense to you? Think about it. Does that make sense to you? That I need more heat to evaporate something than melting it. Does it? Yes or no? Yes. Why? Because when I'm taking it from the solid to the liquid, I just have to take the difference between solid and liquid, that in liquid, the particles are a little bit far apart from that in a solid. In the solid, they are more packed. While when I go from liquid to gas, I need the particles to be far away from each other. They can even take the space in this room. And this is why always the delta H of vaporization gonna be higher than the delta H of melting, the delta H of fusion. And that's the case everywhere for any material. Always you need more energy to evaporate something compared to melting something. Yes. But yes, you would put number of moles times delta H of vaporization. In other words, mass over molar mass. That's right. Okay? So get the idea? Get what equation you're gonna use at what point? Okay, so what I'm gonna do is I'm gonna do one example, then we're gonna go to iClicker, series of iClicker, so that to figure out whether or to see if you get the idea or not. How much energy is evolved when 1,000 gram, so I have a 1,000 gram of water at zero solidifies to ice. So I have clearly from the question, I'm in the liquid phase, I'm going to the solid phase because I'm solidifying to ice. And it's telling me the delta H fusion equals 333 joule per gram. So the first question, which equation are you gonna use? Would you use A, mCSP delta T, or B, Q equal M delta H fusion? Which one, A or B? B, that's right. Why? Because I'm going from water at zero to ice at zero, so it is a change of phase, so I'm gonna use B for sure. Now your second question that should come to your mind, would this Q be negative or positive? Negative, very good. Why negative? Because I'm going from liquid to solid. If I'm going from solid to liquid, I'm gonna heat up the system. That means it is endothermic, Q is positive. So I'm gonna put a minus here, and now minus 1,000 gram, which is the mass, multiplied by the delta H of fusion, which is 33 joule per gram. Gram gonna cancel gram. My answer gonna be 333 times 10 to the 3 minus definitely joule. This is how much I need to solidify ice at 0 degrees. Okay. So let's do an iClicker about this. Okay, so how much energy is required to vaporize 125 grams of benzene, knowing that the molar mass of benzene is 78.11 gram per mole at its boiling point, which is 80.1 degrees Celsius. The heat of vaporization of benzene is 30.8 kilojoule. I'm gonna stop it at 210. Okay, so let's see what you think. Okay, I have 84% for BB is the right answer. So I have benzene, liquid, and I'm going to benzene, liquid at its boiling point, and I'm taking it, I want to evaporate it to benzene gas at 80.1. So mainly it's a change of phase. So I'm going to use Q equal mass times delta H of fusion. My second thought is evaporation. So Q equal mass times delta H vaporization, if it is in a joule per gram, or I'm going to use Q equal N times delta H vaporization joule per mole if it is given to me by joule per mole. Okay? Now the second thing, is it a plus or a minus Q? It's a plus because I'm evaporating, so it's plus. I can see that the heat of vaporization is given by kilojoule per mole, so Q equal N delta H of vaporization, yet I don't have the number of moles, but I have the grams, and I know that the number of moles equal mass over molar mass, so I'm going to substitute it in this equation. I'm going to substitute N to M over the molar mass, delta H of vaporization, which is 125 grams over the 78.11 gram per mole multiplied by 30.8 kilojoule per mole. So my answer is going to be in kilojoule. Why? Because the delta H of vaporization is in kilojoule. So it's 49.3 kilojoule. Okay? Let's do one more. Calculate the energy in form of heat required to convert 225 grams of liquid water at 21 Celsius to steam. What does steam mean? Vapor, gas, at 115. The heat of fusion, the heat of vaporization, the specific heat of capacity for liquid water, and for steam. I'm going to give you 4 minutes 50 to finish this. And I advise you for such kind of questions, guys, don't directly punch the numbers on the calculator. Think right kind of a figure, where do you want to go and to where, from where to where. Okay, so I stopped right here. So I have the most popular answer being B. For those who chose B and they didn't choose it randomly, congratulations. That's a very good job. Okay? Okay. So this question is taken from an exam last semester or the semester before, exactly as it is. So the main mistake that you guys do, not all of you, some of you, that do is just take the calculator, begin punching numbers, and okay, let's match one of them. Guess what? A, C, D, all match for one of the mistakes, for one of the numbers that you're gonna do. So the proper way to do such a question is first draw a graph where we're going and to where. Okay? So first I have water, it is in the liquid phase, and it is at 21. And the question is asking me to take it to the gas phase at 115 Celsius. I can't jump from the liquid to the gas directly. If you just put from here to here and you did the calculation, that's wrong. Because I can't evaporate liquid unless it is in it at its evaporation point or boiling point. So my first step is to take water to liquid at 100 degrees, which is the boiling point. Then from there, I'm gonna heat it up to take it to water, gas at 100. So change of phase. Then when it is in gas, I can heat it up to gas at 115. So I can't go from one phase to the other just directly jumping from 21 to 100. So I have Q1, Q2, and Q3. So the amount that I need is a Q total, which is Q1 plus Q2 plus Q3. I'm going to write the equation for each one of this and then add them together. So for Q1, which equation I'm going to use? M times specific heat capacity delta T, or M delta H fusion or evaporation or whatever. Which one? MC delta T. Why is that the case? Because I'm heating from liquid to liquid, so I'm still in the same phase. So it is 225 grams times. Now the second mistake is not choosing the right specific heat of capacity. You have specific heat capacity of liquid water and of steam. In this case, you are still in the liquid phase, so multiply it by the specific heat capacity of water in the liquid phase. Multiplied by T final minus T initial, which is 100 degrees minus 21 Celsius. If you would like to change it to Kelvin, do so. Add plus 273 minus 273. It's gonna end up the same. Now the answer for this one, for Q1, equal to 74.37 kilojoule. Okay? Is it kilojoule? Yeah. So definitely the number is, you're gonna calculate it, it's gonna be something thousand. I changed it to kilojoule because it's easier to handle the number. For Q2, what do you think? Which equation I'm gonna use for Q2? It's a change of phase. So I'm gonna use mass times, I'm going from liquid to gas, so it is delta H of vaporization. So it is 225 grams, and the delta H of vaporization is 2256 joule per gram, and the answer in kilojoule is 07.6 kilojoule. Now for Q3, I'm going from gas to gas, so it is the mass times specific heat capacity of gas delta T, which is 225 grams, multiplied by the specific heat capacity of steam or gas, which is 1.92 joule gram, multiplied by, I'm going from 115, which is T final minus T initial is 100. And the answer for this one is 6.48 kilojoule. The answer in here is Q total, Q1 plus Q2 plus Q3, Q total Q1 plus Q2 plus Q3, which is the answer 588 kilojoule. Okay? So if you directly said 115 minus 21 and you multiply by specific heat capacity, that's not the right answer. Okay? Now, let's see what's next for this one. Now we're going to start with a new topic after we talked about change of phase. Now we're going to start with the first law of thermodynamics. And the first law of thermodynamics says that the internal energy of a system, the difference between the internal energy of a system, equal Q plus work. Okay, where delta U, I think on owl it's delta E. It doesn't matter whether it is delta E or delta U, they mean internal energy. The difference in internal energy. And, okay, let me write it in a proper way. In internal energy equal Q plus W. So in other words, let's say I have a chemical reaction. This chemical reaction, the change in the internal energy. So the internal energy, we cannot measure the internal energy. Let's say now, I have a chemical. I cannot measure the internal energy of this chemical. Let's say I have methane. I can calculate the internal energy of methane at a certain point. yet I can determine the difference in internal energy of methane before and after combustion, before reaction and after reaction. And to calculate this, so we do the reaction and we find how much Q, how much heat this reaction give or take, and how much work the system give or take. If you remember at the very early lecture about this, we said that if we're doing the reaction using a cylinder and a piston, let's say I have methane and I'm burning methane, the methane can give me heat, can give heat to the surrounding, and can also push the piston up, or the piston can just go down if the volume is changing because of the reaction. And when the piston go up or down, that's work. That's work. So the difference in the internal energy for any chemical or reaction equal Q plus W. Now, let's get started with what is Q, what is W. For Q, we said that if a reaction is exothermic, that means it gives heat, the Q gonna be negative. I think everybody in this class agrees with me with this convention. Now, if the reaction takes energy, needs energy to get started, the Q gonna be positive. So, and you have to keep that in your mind. Exothermic minus, endothermic plus. Now, what about work? One is the work gonna be positive as a sign, one is gonna be negative. So, let's say this is our kind of device. We have a cylinder and a piston. When the work done on the system from the surrounding, what does that mean? That means I'm pushing the piston down. If I'm pushing the piston down and our reaction is in here. Let's say this is the burning of methane is in here. And I'm pushing the piston down, that means I'm putting work on the system because my system by definition is the reaction. And when I add energy, when I push down, I'm adding energy to the system and I'm doing work on the system. And in this case, work is positive. Okay? So the work is positive if the work is done on the system. You need to know those terms, on the system and by the system. Now, by definition, work equals the pressure multiplied by delta V, where delta V is the volume final minus volume initial. So if I do work on the system, that means I put force on that piston. The volume of the system final will be less than the volume initial. That means the system expanded or is compressed. Did it go expansion or compression when I put work on the system? Compression, that's right. So, in other words, if I tell you that the system is compressed or the system undergoes compression, that directly should be work positive. If I tell you that I put work on the system, the work is positive. Okay? Now, if the system, let's take the other case where the system, which is this reaction, is pushing the piston up, which is the red arrow in here, that means it's pushing the piston up. That means the system, which is the reaction, did some work. So the work is negative. That means the system is losing work to the surrounding. And the work gonna be negative. So if the system does work on the surrounding, W is negative. And that means the system expanded or undergoes expansion. Okay? So those are the two terms. Exothermic, Q minus, endothermic, Q positive. If the system expanded or the system does work on the surrounding, W is negative. If W is negative, if the system undergoes compression or is compressed or I did a work on the system, the W is positive. Okay? Okay, why are we doing all of this? Because we wanted to know before and after a reaction or a process, did the internal energy of the system increase or decrease? Okay? Now, when do you think the internal energy will be increased. Okay. Let me rephrase my question. If delta U is greater than 0, is the system internal energy increase or decrease? Increase. Why? Because U final minus U initial greater than 0. That implies U final greater than U initial. That means the internal energy of the system final is higher than initial. So if delta U is positive, that means the internal energy of the system increased during the process. During the process. Now, if delta U is negative, that implies the system, the internal energy of the system decrease. Okay? Now let's go back to the terms of wake being positive, negative, exothermic, endothermic reaction. So let's say Q is positive. What does that tell you? That Q is endothermic and the wake is done on the system. That means this is positive. That means if I put wake on the system and I give the system heat, the internal energy of the system gonna increase. Okay? Now, if the reaction is exothermic, that means Q is negative. So Q negative, exothermic reaction. And W is negative, that means the system expanded. That implies delta U less than 0 and the system energy decreased. The internal energy of the system increased. Now those are the very obvious two cases. It could be one that the reaction is exothermic, the wake is done on the system. Then we have to look at the numbers to see whether delta U is positive or negative. Okay, make sense? Make sense? Okay, so let's do an eye clicker to see if it makes sense or not. Okay, and this is qualitative, so no need for calculation. I'm going to stop it at 110. Okay, so I'm going to stop it right here, check what you think. So I have 69% for B. B is the right answer. So I have delta U equal Q plus W. So during an exothermic reaction, that means Q is negative because it's exothermic. The volume of the system expanded. When it is expansion, that means W is negative. So this is negative and this is negative. That implies delta U gonna be negative, which implies the internal energy during this process of the system decreased. Okay? Now let's do some more on that. I'm gonna stop it at 120. stop it right here, check what you think. Yes, A is the right answer. So delta U again equal Q plus W. So the heat transfer during an endothermic. Endothermic, that means it's a plus. Reaction is 13 kilojoule. During the reaction, the system expanded. So that means the work is negative. And it is minus 20 kilojoule. So delta U equal Q plus W. So plus 13 plus minus 20 kilojoule. Definitely that's kilojoule, which gonna end you up with minus 7 kilojoule. Okay? Let's do more in that. And this time I'm going to stop it at 1. Oh, okay. I'll start right here and I'll check the answer. Okay. So the most popular answer is B. B is the right answer, yet it isn't a big difference between B and C as a percentage. And that's expected. So delta U equal Q plus W. So let's get started. A gaseous mixture was enclosed in a piston and cylinder, which is something like that, having a volume 1545 milliliter. When a chemical reaction occurred, the volume decreased. Is the weight positive or negative? If the volume decreased, that means there is a compression. And if there is a compression, that means the weight is positive. So the weight is plus 1.7 kilojoule. And 1.3 kilojoule of the heat was absorbed by the system. So the system absorbed 1.3 kilojoule. What does that tell you? It is an endothermic process. It is a process that took energy, that needs energy. So Q is also plus 1.3 kilojoule. So the addition of that is going to end up, so Q plus W is going to end up due to 3 kilojoules. Okay, now we're going to start with another topic, which is the definition of a state function. So, by definition, a state function is a function, and by function we mean the process as mathematical process. It is the function that depends on the initial and final state and do not depend on the path. Okay, what does that mean? Okay, the easiest way to think about that is, let's say you have an account, a bank account, and you want to know how much you have between September and November. You need to know, let's say you started with $1,000. Okay? In September, you put $1,000, you've been buying stuff using this bank account, then somebody is giving you money, or you're getting your check, you're adding money, taking money, and so on and so on. And let's say at the end of, by November, you have $750. You can know how much you have in your bank account by a simple way, going online, checking your bank account, and it tells you, oh, now you have 750. So how much you spend between the two is 1,000 minus 750. You just look at the end one, and the initial one, and the final one. let's say you don't have internet, your bank is not a good bank, they don't have online banking, and what you have to do is to track it yourself. What you're gonna do is say, okay, 1,000. The first day I spent $250, so minus $250. The next day I get paid $350. Then I went to the restaurant, and you keep doing calculation until you get how much you have. But at the end of the day, the difference between the two accounts, initially and finally, between September and November, it's not gonna change depending on how you're doing the calculation. As long as you're doing the calculation right, it's gonna be right. You're gonna get the number right. Okay, you may say, okay, what she's talking about? That's definitely obvious. We're gonna depend on that thing on chemistry. We're gonna use this kind of thinking in chemistry. So sometimes in chemistry, we don't know how much is the heat of one reaction. So what we do, we use 4 or 5 other reactions, and then we add them together to give us the reaction that we wanted to calculate the heat for by using this process. That means as if we don't have online banking, so we have to do this plus minus plus minus. Another example is the following. If that doesn't work for you, let's say I have mountain A and B. If I ask you what is the difference in the height between A and B, you can simply say, okay, okay, that's much. The height of this that much. HB minus HA, I get the height. Another person say, oh, you know what? I'm gonna go from this hill, go all the way, then measure how much and do the difference. It doesn't matter how you do the measurement. At the end of the day, HA, the height of A and B gonna be the same. Okay, we're gonna apply that on Monday, and we're gonna start with Hess's law. Enjoy your weekend, guys.